It all started over 2,000 years ago when the very first water wheels were developed. These wheels were not initially mounted on a nice straight and smooth beam for an axle. They would have been propped over a moving stream on whatever semi-straight log was available. The axle supported the wheel and connected it to whatever mechanism needed power. Saw and grain mills were some of the first things connected to this power source and were very useful. One day, someone must have noticed that these tree branch stumps on the axle jutted out and probably just held a stick against them. As the log axle rotated and the protrusion hit the stick held against it, it pushed it down. It didn't take long for ancient engineers to figure out that you can build a big hammer, mount it on a pivot, and let the bumps on the axle hit against it. And just like that, you had a big, heavy hammer that would drop down with more force than any one human could muster. Our world today is consumed by the digital. AI writes our emails, drones drop snacks into our yards, and smart toasters can text you when your bagel is ready. All this overwhelming technology made me wonder, do machines have to be digital in order to have memory? And where did the simplest and earliest forms of mechanical memory come from? We often think of memory as the ability to recall information, names, and dates, but the earliest machines to have memory used physical geometry instead of silicon chips to store logic. This is the story of the origins of mechanical memory, how it transformed our world, and why we still need it today. In this video, we will focus on a very specific subtype of mechanical memory, which I am going to call rotational memory. Simply put, rotational memory is the ability to encode and decode information or actions in a rotating object. The log axle had issues though because the bumps were random, and random unplanned actions must be eliminated in well-designed machines. The log was replaced probably very quickly with a straight beam, and wooden cam protrusions, known then as tappets, were mounted into the beam at precise intervals. Simple wooden gearing was also introduced to control the speed, and now the hammer would rise and fall at the desired tempo. These early machines gave birth to mechanical memory, which would ultimately be digitized. Let's think about those tappets on the axle from that viewpoint. Each protrusion can be thought of as the 1 in computer programming, and the space between them as the 0. 1, 0, 1, 0, on, off, on, off. Adding more tappets in the same rotational plane would increase the speed of the hammer and the length of the very basic programming. I say basic because the only thing you can really program into these is timing, not information. These early machines excelled at slow, labor-intensive tasks. One of the best ways to appreciate the creativity of these machines is to look at the plans from medieval and Renaissance engineers. There is probably no greater online resource than archive.org, and everything I show here is just a tiny fraction of the many beautiful books on mechanics from this time period that you can read there. Basic as the triphammer program was, the ability to tell a machine, "This is what I want you to do, keep doing it until I tell you to stop," is indeed a form of memory, albeit just barely. However, triphammer-style tappets that push up or down on something set into their path have a serious limitation. The gap between the tappets means the resulting motion will be intermittent. The tappets for a single machine attachment should be evenly spaced. If not, the tool they act upon does not have time to repeat its full cycle. Anticipating a nice rhythm of the tool is desirable, but what if you don't want intermittent motion that is only up or down or left or right? What if you want continuous or complex motion, motion on the X and Y axis or X, Y, and Z axis? This is where you are going to need a cam. I differentiate between tappets and cams for this very reason, intermittent versus continuous motion, although cams can pretty much do any type of motion you can think of. So when I use tappet, I don't mean in the modern engine context, but rather in the medieval millwright context. A cam stores continuous motion in its physical geometry and imparts that motion to a follower of some sort that presses against it as it rotates. The follower is the part that stays in contact with the cam and translates its shape into motion. The path the follower should make must be reverse engineered by careful considering of the desired end result, and then engineering that exact shape that will, when rotated, play back the correct combination of movements against the follower. Too many sharp angles on the cam and the follower will get stuck. As the field of mechanical engineering grew, So did the ways to transform rotational power into various motions. To understand this, we need to differentiate between these mechanical systems with analog memory and which ones are simply ways to change the direction of power. Let's think about these systems as branches on a family tree. We will start with the tappet here at the bottom, as it does both power delivery and basic memory in the form of timing. Out of that main trunk, the early rotating systems of the tappet and axle split it into two main branches: energy shaping in the form of the crank, and information shaping in the form of the cam. The crank paves the way for the crankshaft, which is a shaft with one or more cranks that convert reciprocating motion to rotational, or vice versa, across multiple linkages. The cam on the information side paves the way for the camshaft, which is a shaft carrying multiple cams to coordinate time motion across multiple outputs. As many of you know, both are absolutely integral to the modern combustion engine. We must not think that the main branch of Tappets, power delivery and timing, did not advance as well, though. The massive thumping triphammer lived on in miniaturized form in the music box and its pin cylinder, or in the chimes of a clock, like this one I had disassembled for parts. The placement of the music box pins on the cylinder are the memory, but since the pins physically strike the notes on the harp keys, they also have a physical action. But unlike the cam, the motion imparted is not continuous. Clock and watchmakers have always loved the cam, but it has never been taken to such perfection as in the mechanical automatons of the 18th and early 19th century. Many brilliant watchmakers used cams to program complex actions into their creations, but no one, in my opinion, did it better than Pierre Jaquet-Droz. His machines, the writer and the draftsman, are still two of the most complex automatons ever made, making use of two brilliant cam-based systems: the combined cam system and the vertical cam stack. Think of the problem of how to use a cam to create a complex motion, such as that of moving a pen to write the letter A. You can break the profile of a cursive letter A down as follows, but you can't just cut those curves into a metal cam and attach it to the arm holding the pen. The reason for this is while the pen does move, it will write on top of itself because the cam can only push or pull in its place. If you take the pen yourself and start writing large exaggerated letters while carefully observing your hand, you will notice that at any one point while writing, the tip of the pen is tracing a combination of vertical and horizontal inputs when looking down at the paper. It does not just move in the X or Y coordinate space, but rather in a blend of them. So for an automaton to create a complex shape, you would have to combine the motions of at least two cams. There are several brilliant ways this can be done, but most are based on different ways to physically link the cams. One way to do this is to combine multiple cams together in what is known as a 4-bar linkage. A 4-bar linkage consists of 4 links that are connected in a loop by 4 joints. These linkages are commonly used in a wide variety of mechanical designs, such as automobiles, robots, and other machines. One of the main advantages of 4-bar linkages is their ability to convert linear motion into rotary motion, or vice versa. They can also be used in robotic arms and other types of machines that require precise and controlled movement. However, the motion of this automaton is not a closed-loop system with one degree of freedom. It is a compound cam follower system with orthogonal motion summation. Orthogonal motion summation just means it takes the up and down motion of one cam and combines it with the left and right motion of another cam, creating ideally one smooth flowing output. In this book named Automata, a historical and technological study, the authors state that the original writer automaton by Pierre Jaquet-Droz used polar coordinates rather than rectangular coordinates. This is best understood as a description of the mechanical geometry of the linkage, not the way the cam encodes motion. The cams themselves still functioned in a time-based manner, each one producing a controlled displacement as it rotates, effectively encoding motion as a function of time rather than directly tracing a shape. In total, this automaton used the following cam systems. One cam set controls the primary movement of the hand in one direction. A second cam set controls the orthogonal or complementary motion. A third cam set controls the downward pressure or pen lift, allowing the machine to distinguish between light and heavy strokes and to lift the pen between segments. All these cams were adjustable for fine-tuning. This lower mechanism advances a vertical indexing disk one step, effectively selecting the next program character. Attached to this disk are a series of adjustable wedges, each corresponding to a letter and set to a specific height. As the disk rotates, the next wedge comes into position and acts on a set of levers, which shift the cam cylinder laterally so that the new set of cams aligns with the followers. This repositioning determines which letter will be written next. As the machine writes, the cam stack moves, not the followers. The followers stay essentially fixed in position, continuously pressed against the cam cylinder by springs or their own weight. When the machine finishes a letter, the indexing system below, the disk with the adjustable wedges, acts through a system of levers to translate the entire cam cylinder laterally, effectively up or down along its axis. This shifts a new set of cam profiles into alignment under the same set of followers. In other words, the followers do not step from cam to cam. Instead, the program, the cam stack, is repositioned beneath them, bringing the next letter's cam into contact while the followers remain in place. If we go back to our mechanical memory family tree for a moment, we can add a few branches. Cam-based memory naturally splits in two very different directions from here, and the Pascaline mechanical calculator sits right at that fork. I know the Pascaline predates the Droz automata, but this is not a diagram that shows branching through historical time, just the branching of the concepts. In the cam system, like those used in automatons, information is encoded continuously. The radius of a cam at every angle represents a position over time, producing flowing analog motion. The Pascaline takes that same core principle, geometry storing logic, but discretizes it. By discretizes it, I mean the Pascaline takes the idea that shape controls behavior, but turns it into a system where the behavior happens in countable steps instead of smooth curves. Instead of a continuous profile, it uses an indexed wheel position where each tooth represents a fixed numerical state. A full rotation is no longer a waveform, but a count from 0 to 9. We are touching the boundary between smooth analog action and proto-digital computation. This excellent YouTube video greatly helped me understand how mechanical calculators in general work. If you want to fully understand this particular machine, I know of no better place to learn it. This man spent 8 years building a massive calculator out of wood based on the arithmometer design. What makes the Pascaline a true descent of cam-based rotational memory is that the entire computation is still physically stored in the arrangement and relative positions of the rotating elements. Each gear tooth is a unit of memory, each rotation a cycle of time, and each carry event a conditional operation stored in metal. Where cam systems excel at reproducing complex motion like handwriting, the Pascaline excels at the symbolic manipulation of numbers. But both rely on the same deep idea that information can be embedded in rotation and read out mechanically. In that sense, the Pascaline represents a critical transition from analog mechanical memory to discrete mechanical computation, laying the groundwork for everything that follows. If we go back to our mechanical family tree, we will see this trunk, the descendants of the Tappet and triphammer, is looking a little bare. The last thing we spoke about in this vein of mechanical development was the pin cylinder used in the music box or barrel organ. Now take a look at this large machine. This is the Vaucanson Loom that was one of the many mechanical items I was lucky enough to see in person at the Musée des Arts et Métiers in Paris a while back. I am fortunate to understand a bit more about historical looms and weaving than the average person because I grew up in a household with about a dozen of them, ranging from tiny tabletop ones to ones so large they needed their own room. My mother is a historical weaver and one of the last in the United States who can create these complex patterns entirely by hand. As a child, I was always fascinated by these interesting machines and did a small amount of weaving on a tabletop loom as I grew older. In any case, I know a lot about how difficult it is to program a complex pattern into a loom. You have this absolutely bizarre programming language, which I could never make heads or tails of, and then there is the actual task of threading the loom, which is how you program the pattern by hand. The most basic loom functions on the following concept. You have all these individual threads, and you wish to join them together to make cloth. To do this, you need to lock the threads together going this way with another going this way. The loom holds a set of threads called a warp under tension in frames called a heddle that allows each set to be raised and lowered independent of the other. As each heddle is raised, a horizontal thread called the weft is pushed between the upper and lower sets of threads with a device called a shuttle. After each pass, the fabric rows are compacted with this device called a beater. As you can see, weaving was not only a complex activity, especially in the 18th century Europe, where fashion was driven by unique patterns, but it was also very labor-intensive. There were multiple attempts to take the cylinder from a barrel organ and use it to automate the entire process of weaving, the most notable by Basil Bouchon. Bouchon's loom used perforated paper to hold the pattern for the loom, but it didn't work very well. Vaucanson was one of those true genius inventors that comes once in a century if we are lucky. Machine Thinking did a phenomenal video on Vaucanson's 1751 lathe that the rest of machining history is built upon, and inspired me to go to Paris myself and see this museum. So many thanks to that channel. Vaucanson came along and used his prodigious brain to correct the previous half-working attempts at loom automation. Remember, the music box is a maximalist version of the triphammer. The limitation was the number of pins a music box could have on the surface of the cylinder. Vaucanson realized that the pattern of the pins and the pins themselves could be divided into two parts. Instead of protrusions on a cylinder, he wrapped that cylinder with strong paper that had specially punched holes in it. The holes are the memory, and the memory is read with needles that either fall into a hole or don't as the paper rotates on the cylinder past them. This division of memory meant that unlike a music box that had to impart kinetic motion to the harp to strike the notes, the loom's pins moved in and out of the pattern, reading and responding to the program instead of being forced to play by the cylinder. A further loom refinement was done by Jacquard, and his loom is much more famous, but there was much debate in the French scientific community regarding if he was deserving or not of the praise, or simply good at taking the work of others and repackaging it. This so-called War of the Looms had far broader societal and industrial impacts than we can discuss in this video, but in its creation, the steps of the machine age can be heard clearly. The Jacquard loom took the Vaucanson paper program and made it more robust by using strong cards linked together. This was more sturdy and less likely to tear, and made the machine far more commercially viable. These developments in mechanical memory blur the branches in the family tree we've been making. No longer must memory be confined to the circumference of a single object, or sets of objects like the Droz cam stacks. Those are both inherently constrained by a reasonable circumference. If your program was 30 feet long of instructions, a totally reasonable size for a complex silk weaving pattern, then a wheel of about 9.5 feet would be needed to hold all those instructions in music box pin form. With the instructions being moved to hole punch cards or paper and the reed head being fixed in place, an unlimited length program could be developed. Memory could be moved outside of the confines of metal, and the creative broadness of the human mind could be more readily expressed. In spite of all these advancements, these types of memory were just that, the ability to regurgitate information, not the ability to take in information and interact with it at a deeper level. These were not computers in the strictest sense, but they were paving the path. The first machines that could be safely said to be mechanical computers were the two designed by Charles Babbage in the 19th century. The first was known as the difference engine and was basically a very advanced computer used to compute polynomial tables. His second machine, the analytical engine, was more of a general-purpose computer, but people can debate that. Ada Lovelace, a British mathematician and the first true computer programmer, worked with Babbage later on to program the analytical engine's algorithm. The difference engine scales all the concepts we have been discussing into something far more ambitious. A machine that doesn't just store numbers, but automatically generates new ones according to a mathematical rule. Its operation is based on the method of finite differences, which allows polynomial functions to be computed using only addition. Mechanically, the machine is built from vertical columns of digit wheels, each column representing a number or difference in the sequence. These columns are arranged side by side, and the machine proceeds through a repeating operation cycle. First, it adds the value of one column to the next, propagating the results across the machine, and then it advances the system to prepare for the next step. In this machine, timing is everything. Operations are broken into phases so that carries can ripple through one column before the next operation begins, preventing mechanical conflict. In this sense, the difference engine reintroduces something very much like CAN-based memory, not to store the numbers themselves, but to store the sequence of operations. acting like a kind of mechanical program. Each rotation of the main shaft corresponds to a full computational step, during which additions, carries, and transfers occur in clearly ordered choreography. The result is that after each cycle, the rightmost column produces the next value in a polynomial table automatically. What makes the machine extraordinary is that it embodies both forms of mechanical memory at once. The state of the computation is stored in positions of the digit wheel, discrete rotational memory, while the procedure of the computation is stored in the timed mechanical interactions, a kind of cam-driven operational memory. In effect, Babbage's engine transforms the idea of rotational memory from something that reproduces motion into something that generates knowledge, marking one of the clearest conceptual steps towards modern computing. Although, as I've mentioned before, others will say this is just a glorified calculator. However, since this machine starts with an initially calculated polynomial value, the input, and then uses the finite differences method to compute nearby values, the output, it can also be argued that it is a computer. Babbage was still building his second difference engine when he decided to improve it and build the analytical engine, a machine solidly in the computer world. Mechanical memory had now reached its fullest form, where every type of logic and motion memory we have discussed before was implemented. Its brain consists of two major structures: the store, which very predictably stored the memory, and the mill, which processed the information, conducted calculations on its own based on programming. When it comes to how the machine was fed information, we should feel instant familiarity. These cards are to program the analytic engine, and these are from the Jacquard Loom. Punch cards were used as a reliable way to feed information into a computer well into the 20th century. This is where Ada Lovelace played a crucial role. Working from Babbage's designs, she translated and expanded an Italian paper on the analytical engine and added extensive notes that went far beyond explanation. In those notes, she described how the machine could manipulate symbols according to rules, not just numbers, an extraordinary leap forward in thinking at the time. She also wrote what is considered to be the first computer program, outlining how the machine could compute Bernoulli numbers step by step. More importantly, Lovelace recognized that the analytical engine was not just a calculator, but a general symbolic processor, capable in principle of handling music, graphics, or any other structured information. This conceptual insight is why she is often regarded as the first computer programmer. Ada Lovelace clearly articulated a conceptual leap that Babbage did not express as explicitly or as broadly, that it was a general symbol manipulation system. In her notes, she wrote that the engine could operate on things other than the number, if those things could be represented symbolically. Another way to say this is that Lovelace implemented the use of algorithms, sets of instructions, into mechanical computing. Babbage absolutely understood programmability via punch cards, loops, and conditional operations, as well as the separation of memory and processing. But he was focused on the mechanical systems that did these calculations, not on the broader implications for the future. Babbage welcomed the input of Lovelace and called her the enchantress of numbers, showing that for all the reports of his difficult personality, he was able to recognize and appreciate native genius when he saw it. In modern terms, the difference engine is a dedicated calculator, while the analytical engine is a fully programmable computer architecture. This shift from fixed mechanical computation to programmable logic marks one of the most important conceptual breakthroughs in the history of technology. So why, you may ask, should we care or talk about mechanical memory? Surely it's an incredibly outdated and barely useful concept in today's digital environment, outside of engines. Far from being obsolete, rotational cam-based mechanical memory is used extensively today. One field that uses these in many ways would be industrial manufacturing. Packaging machines need mechanical memory to organize filling, cutting, and sealing processes. Assembly automation lines use cam drums to coordinate dozens of physical actions. Bottling and capping machines run at insane speeds and need hard-coded mechanical timing. While not all of these processes use cams, mechanics beat software latency every time. Mechanical systems are often enhanced and monitored with digital systems, but the core beating heart is still mechanical. Even modern CNC and hybrid machining tools use cam paths to control arm motion sequences. It is often far quicker and easier to switch CNC cutting tools with a predefined cam path versus, say, a robotic arm. Outside of industrial manufacturing, many items in your house use mechanical memory, often hidden inside. Washing machines, some modern, many basic, have entire wash cycles encoding cam stacks. Ice makers in your fridge are still widely cam-driven. Windshield wiper mechanisms use cams to control intermittent timing. If you visit a theme park, many of the moving animatronics, such as those that jump out along a ride and scare you, use cams. If you're someone who grew up on a farm like myself, you'll be aware of farm implements like seed drills that use cams to drop seeds with exact timing, and hay baling machines that use mechanically encoded memory to rapidly tie knots in rope around the bales. Clocks, watches, and surgical tools, medical infusion pumps, nuclear fail-safe systems, and mechanical timers for explosive safe environments such as oil and gas. You really can't look at any industry without seeing mechanical memory. Engineers definitely have options when building systems, but the choice to use CAM-based versus software-defined symbolic memory is not arbitrary. The choice is driven by a consistent core question engineers ask. Do I want fixed, repeatable, guaranteed behavior, or flexible, changeable behavior? Fixed, repeatable behavior would suggest a mechanical solution. If you want various modes, adaptation to inputs or conditions, then you want a hardware and software solution. The CAM can't be reconfigured later, but the software interprets inputs at runtime and adjusts. It's not that one is better than the other. Each has its own set of advantages. CAMs are chosen when failures must be predictable and gradual. If the environment is harsh, heat, vibration, or radiation, and you want little or no dependency on electronics, then CAM-based or other mechanical memory is better. If your system can tolerate a non-deterministic failure and redundancy and diagnostics are available, then software solutions may be better. When a CAM wears a bit, it can still perform, just worse. If there is a software glitch, a controller can crash and stop everything instantly. However, in this modern world, engineers happily accept the best of both worlds, and hybrid systems seamlessly combine CAMs with software. Programmable logic controllers are often paired with CAMs to set a baseline timing, but then have a software layer for remote overrides. The CNC machines I mentioned before that use CAMs for tool swaps, there is a layer of digital control as well. CAMs are used when an engineer wants a machine that cannot forget what it's supposed to do. Software is used when you want a machine that can change its mind. We have come a very long way from that early log, attached to a water wheel bumping crudely into the triphammer, its thud being the first echoes through the once quiet village that the machine age is on its way. The path to modern digital and hybrid memory was built step by trial and error through the genius of the ancient and medieval engineers who wrestle with how to program machines to better their lives. Their actions paved the way for us today. The history of mankind is the history of tools and machines, but we often forget those all-important linkages from past to present. Building a family tree for technical concepts is one way in which we can identify new branches that are not fully developed. Perhaps some smart person will think of new forks, new ways to split off logic and memory, or a new concept altogether. It is great to understand the digital computing of the modern era, but as we jointly enter this challenging world of artificial memory, it feels good to once again anchor ourselves in the mechanical, in the tactile. AI does not have hands nor feet. If it wishes to move something, it is going to need a physical interface to the world. Cams and gears will continue to be the durable, beating heart of machines for many years to come. Thank you for watching.